Non-destructive testing covers a wide range of techniques used in industry and science, and the samples are evaluated in terms of their material property without causing any damage, and is therefore often carried out in the workplace.
Non-destructive testing is extremely important to industry because it allows the component to be used after it's been tested. Okay, what we've got here is dye penetrant testing, a very simple test, and it's used to detect open pores or cracks that break the surface. This is quite important because if these defects go undetected, it could lead to some catastrophic failure and potentially deaths. We've got the dye, we've got cleaning fluid, okay, and we've also got some developer, like a talcum powder substance. It's a very simple technique to do, so you'd be using it in aerospace, you'd be using it in railways, you'd be using it in heavy industry. The uses are pretty much limitless. So first we need to clean the sample to get rid of any grease or dirt. And then we're ready to apply the penetrant. And then you've got to give it sufficient time for the penetrant to seep into any surface breaking defects. The finer the defect you're trying to detect, the longer you need to leave it. Okay, so this has been sat for about 20-30 minutes. It should be sufficient time for the penetrating media to seep into any open voids. Okay, so the next stage of this is we've got to wipe off any excess penetrant. We get a rag, some of the cleaner, spray the cleaner onto the rag, and then just wipe off any excess. Nice and simple. The next section is to get the developer, and we give the surface a nice liberal even coating. Okay, so we've left this sample 10 minutes to develop, and what we can see is there's a crack emanating down the middle of this sample. You can see that, all the red that's coming out. You can also see it around these holes and around the edges, and that's just where we didn't clean inside the holes and inside the edges. So that penetrant is then being sucked back into the developer. What we've got here is one that came in from testing. This is a real life component. This is the bottom of a glass mould, and on the back of that we've done a dye penetrant test, and you can see about 4 nice fine cracks that run all the way through that specimen. Okay, so that's dye penetrant testing, a very nice, cheap and quick way of detecting defects without damaging the actual component or material. Okay, the next test we're going to do is magnetic particle inspection, and for that we need a fluid containing some magnetic particles, we need a background contraster, and we need a cleaner. We also need a magnet. Now we've got an electromagnet here. You can also use permanent magnets, although there's difficulties taking them off if you've got nice strong magnets there. So the advantage of this technique over dye penetrant testing is that you can detect slightly subsurface defects. The main disadvantage is that you've got to be able to magnetise the material. So non-magnetic materials you can't test using magnetic particle inspection testing. So the first thing we need to do is clean the sample. And then the next stage is to spray on your contrasting background, and then give it a nice even coating. Then we need to leave it to dry before we can apply the ink and the electromagnet. Okay, the sample is now dry, so we need to bring the sample in contact with the electromagnet. And we need to make sure we get good contact there. Turn on the electromagnetizer sample and we spray on the magnetic ink. So what's happening here is we're inducing a magnetic field into the material. If there's defects within the material, those can deviate the lines of magnetic field, and that's where the magnetic ink that we sprayed on will congregate. And that's what we can see here. If we'd have been testing this component in industry, because we've identified these cracks which are detrimental to the component, we'd just probably throw it away. If we didn't see any cracks, if it was deemed as good, then we'd have to make sure that we cleaned it off so that any materials on here are not going to contaminate the component for further work or its service life. Okay, just to recap then, the dye penetrant test allows us to detect surface breaking defects. The magnetic particle inspection allows us to detect slightly subsurface defects. And what we've got here is ultrasonics, and that allows us to look right inside the material. Okay, so this is a sample. This is his ultrasonic probe, and this is where we can see the signal coming back and detect any potential differences in the material. So this is exactly the same sort of technique you'll see in a hospital, maybe looking at babies, maybe looking at kidney stones, that sort of thing. Okay, first of all, we need to put on a couplant, and this is something that excludes air from the sample and the probe. Sound doesn't travel very well through air, so we need to exclude as much of it as possible. Once we've got the couplant on, we pop his probe on top and then give it a wiggle round to exclude any air. Okay, so the width of this screen is the equivalent of 100mm depth. Now at the end of this screen you can see there's a spike there, and that's the reflection from the back wall of the sample. As we traverse along this sample, what we'll start to see is a spike appearing at about 45mm there, which is a reflection from this top surface here. As we continue to traverse, we get a reflection about 15mm, and what that is a defect 15mm down from the surface. Again, continuing the traverse, because that's only a small defect that disappears, whereas we're still detecting this defect that's 45mm down. If we carry on traversing across, eventually the one at 45mm disappears, and then we start getting the back wall signal reappearing at 100mm. What makes ultrasonic testing different to some of the other non-destructive testing techniques you've seen is that it can detect defects, maybe gas porosity, little bubbles or tiny cracks within the material, but those could be meters away from the surface of the material. And that makes it a very powerful technique.
This is a scanning electron microscope. This is the most sophisticated bit of equipment we have in the Materials Research Institute. The scanning electron microscope enables us to do 2 or 3 things that we haven't been able to do with optical microscopy. The first is that we can now look at material at very high magnification. An optical microscope will only go up to about 1,000 times magnification. With the electron microscope, we could be looking at 500,000, 800,000 times magnification. It's no good just making things bigger if you can't then resolve the detail. The electron microscope gives us extremely good resolution at very high magnification. It's actually made up of some very small, simple ideas, which if you bring them all together, make it into an incredibly sophisticated piece of equipment. At the top of the column, there's a tungsten filament. That filament is heated up, and that gives off electrons. The electrons come down the column, they're focused by the electromagnets onto the surface of the sample. And there they do 2 things. One is they create the image that we see on the screen, and the other is that they allow us to do some chemical analysis of the sample if we need to. Basically put, the electrons hit into the surface of our sample fairly hard and knock out electrons from the surface, which are characteristic of the element which the sample is made from. With this bit of equipment, we can really get to almost the atomic level to say what's controlling and influencing the material behaviour. As a materials engineer, I love this piece of equipment because we can do so many incredible things with it. We can use it to develop new materials, we can use it to enhance existing materials, and we can even use it to solve crimes in forensic engineering. Forensic engineering uses the fundamentals of maths, physics, and some inorganic chemistry to inform and augment legal argument. A classic forensic investigation that we get involved in here is where there's been a road traffic incident. 2 cars have collided. One claims that it's the other car's fault because he didn't have his lights on, and therefore they couldn't see them. The police bring the broken lamps to us and ask us if we can establish whether the lamp was illuminated just prior to the collision. And we can do that using our electron microscope. So the chamber's now evacuated. We've turned the electron beam on. Let's have a look and see what we can see in the electron microscope. What we can see here is the tungsten filament removed from the vehicle, and the first thing we notice is that there are these globules on the surface. When we do the chemical analysis of those globules, we identify them as silica, and that silica is from the glass bulb which broke during the collision and showered down onto the filament. The fact that they're globular tells us that this filament must have been hot when that glass landed on its surface. The filament being hot tells us that the filament was illuminated, and therefore the motorist who was driving this car was not guilty of driving without the lights on.